I like the unknown things, right? What are we going to discover that's going to lead us somewhere unexpected? We are now pushing the limits of our technology with this system. And every time you advance technology, it improves the economy and the lives of people. And that provides the tax dollars that we need to keep letting this stuff happen.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. In a moment reflecting decades of vision, innovation, and the power of federal investment in science through the U.S. National Science Foundation and the U.S. Department of Energy, the NSF-DOE Vera C Rubin Observatory has officially started the 10-year legacy survey of space and time, marking the beginning of a new era in astronomy and astrophysics. We're joined today by Edward Ajhar, NSF Program Director of the NSF-DOE Vera C Rubin Observatory, whose Sentinel-like mission is expected to yield a staggering number of new discoveries. Billions of stars and galaxies, millions of supernovas, and comparatively nearby objects in our own solar system, including millions of asteroids and untold numbers of comets and interstellar objects just passing through. Dr. Ajhar, thank you so much for joining us today.
Oh, you're very welcome. Happy to be here.
So I'd like to start with the big definition question. What is the NSF-DOE Vera C Rubin Observatory?
It's a big question, right? Because it is not just a telescope, it is a whole system. And we'll start right where it starts collecting data, which is the telescope. So it's an 8.4 meter telescope, which is one of the largest, among the largest in the world. But it's a very special one, which we can talk about more. And that is connected to the largest camera in the world, which is 3,200 megapixels. And then that collects the data, and it goes to now another really important part of what this system is a huge database of the data that it's going to collect. It collects it fast, analyzes it fast. And it's got to rely on a big network that goes from South America all the way to Stanford University, where SLAC is, and where the data are analyzed. But I think the most important part of that system is all the people that make it work too. So we have a lot of education and public outreach people and all the scientists and engineers and technicians who keep it all running. So it's a big, powerful staff and a big, powerful system. And it is designed to take a survey of the entire southern sky. And it's able to do this twice a week, which is really incredible. So it's designed to be fast. It's designed to be take a wide field pictures and do a lot, process a lot of data quickly.
And I think we'll get into a lot of the various aspects of this as we go through this conversation today. What makes the NSF-DOE Vera C Rubin Observatory different from other optical telescopes?
Well, first of all, again, we'll start with the telescope itself. So I mentioned that it's an 8.4 meter telescope, right? That's it's almost 30 feet across, right? And that isn't the biggest one. There's other telescopes that are 10 meters, so they're bigger. But what makes this one special is this piece of glass has two separate mirrors configured in one piece of glass. So it's got the outer ring, like a donut, is we call the primary mirror. It's where the light first hits the telescope. And then it bounces off that surface and goes up to a secondary mirror, and it comes back to the same piece of glass, but this time on the inner part of that donut, which has another shape of glass, which is the tertiary mirror, because it's the third time the light hits it. And that combination and the way the optics are designed of all these three pieces, these three mirrors, that's what creates and allows this very wide field of view on the sky. So if you imagine what the full moon looks like on the sky, one image from this telescope can capture 45 full moons worth of sky in one shot. It's just really astounding. So to do that really requires a very specialized telescope. If you've seen other telescopes, this one's much shorter. I mean, it's a stubbier thing. So as wide as it is big, it isn't as tall as it is wide. So it's really unusual among many telescopes. So it is designed to be fast. It is designed to be very firm, so that when you move the telescope from one pointing of the sky to the other, because it's going to be doing that all night long, it's got to be able to settle down quickly so that you can take this survey very efficiently. So it's going to do this survey for 10 years. So keep looking at the whole sky for 10 years, and twice a week covering the entire sky. So we take like 30-second images, move on to the next part, take another 30-second image, move on to the next part of the sky, and just do this for 10 years. It's quite incredible, and it will find us many things, which we can chat about some more.
Is there a reason that, for the 10-year time frame versus 2 years or 5 years or something? Is there something about that length of time specifically?
Well, this is always a kind of technical question almost because a lot of times people think, well, the bigger the telescope gets, the further away you can see, and that's not really. I mean, there's an element of truth to that, but it kind of confuses what's actually going on. What we really want to do, the most distant objects you can imagine are some of the faintest ones, and so to collect light from something really faint that's very far away, you need a big piece of glass to collect the light, as much light as you can from that object, and then to be able to resolve it into something that you can distinguish one part of that object from another part, so it's not blurry. So you make bigger pieces of glass to do that. And then the other complication is, well, the sky is throwing light and it's on the background, it's around that object. So the combination of doing all of those things, you could stare at an object that's a faint object like that with a telescope that's not as big as Rubin's, but you can't combat all those other problems of, well, how long do I have to stare at it to get an image that's faint enough, and resolved enough and has enough power for us enough signals from that object in order to really resolve it and analyze it. It's that combination. So why 10 years? Well, you could spend, in over those 10 years, each part of the sky is going to be observed about 800 times. So 800 30-second exposures. They're in different filters, so it's a little more complicated than that. But essentially, it's like 400 minutes on one object, or on each part of the sky. If you had a smaller telescope, you'd have to spend much more time on it. To see those same objects with a smaller telescope would require many, many, many more years. And so the smaller your field of view is, or the smaller your telescope is, all these things compete to make us want a longer survey. And then, depending on the size of your telescope, you will have to observe. You might have to observe 100 years, right? But it still may not be quite the same quality. So you have to find what's the optimal way to see the faintest objects we can see and advance the field, because now there's surveys of the sky. Astronomers have been doing this for a long time because we get so many benefits from them. But this will be the one that goes fainter, far fainter than any other telescope and any other survey that's ever been done. As I said, if you had a smaller camera or a smaller telescope, you could take you 100 years to do the same survey, which is not very practical. So the whole thing is designed about doing this fast, deep survey in a reasonable amount of time.
So thinking about this much data, is there a reason to have other optical telescopes once this is in effect?
Yes, thanks very much for that question, because this is something that's really not as obvious to the average person as you would like, right? What this camera and a telescope do as a system is give us a very deep image that I've been talking about, right? We get to very faint objects. And I talked a little about filters, right? So there's different parts, from the blue end of the spectrum to the red end of the spectrum. If you think of the rainbow, right? This will cover that whole range very well in the 6 different colors, essentially. Well, that gives you some information, so you can look at any particular object on the sky and you'll have a color. You'll say, is this red? Is it blue? Is it green? Is it? You'll have a whole range of color, but it's not a whole lot of information. So if you really want to learn about that object, what we do is take a spectrum of it, right, where all the light is now broken up into many, 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 many little pieces. Instead of 6, think of thousands of pieces, or tens of thousands of pieces. And that tells us the chemical composition of that object and many other things. So that's how we learn so much of what we know about our universe, is by taking a spectrum of those things. So other telescopes will follow up on objects identified and cataloged in this with this survey. They could be 8-meter telescopes, but then we have instead of having a 3,200 megapixel camera attached to it, we have a spectrograph that's tuned to learn different things about that object that we need to understand what's going on. And one thing that we will learn, we look at clusters of galaxies this way, and you can take a lot of spectra of those galaxies and learn about the evolution of galaxies in the universe over time. And we look at individual stars the same way, or comets or asteroids. We need those other telescopes to do that. And for brighter objects, you don't need a big 8 or 10 meter telescope. You're happier with a 2-meter telescope or a 4-meter telescope to learn things. So we tune the follow-up to the appropriate tool. It's just like doing anything. You use the right tool for the right object. This thing is one tool, and the astronomers toolkit and a very important one, but you need other ones to do the next steps of analysis and learning about our universe.
There was a point in there that made me think of a question that I was asked at one point, is like general population having some confusion for how people know what planets that are far off, what the composition is. And when you're talking about the different spectrum, and that's how you might recognize that it's a gas or a liquid or something.
Exactly. Yeah, that's it. Each element has a different signature that comes through in different lights, and that's how we learn about how much is there. And we learn temperature, we learn how fast things are moving, we learn many things from other types of observation, and those are harder to do, right? We couldn't do, like, we're going to catalog about 37 billion objects with this survey after 10 years, but we're not going to have 37 billion fine spectra, right? So, if you could really follow up, you'd want to have a spectrum of every single object that you found. But that we don't have the capability you're doing right now.
Maybe later. I would like to pivot a little bit to talk about the development. This project has been a long time coming. Can you talk a little bit about that timeline and how long this has been going on when you came in?
It really goes back to the late 1990s. And that is a time when the idea of dark energy was just coming into being, really. The idea of dark matter was already very hot topic. And so this was originally dubbed the dark matter telescope, and which kind of led to the naming of after Vera C. Rubin. From the late 90s, you start getting this idea, and one of the telescope designers had the idea of, well, we could make a piece of glass, right, that could have both of these surfaces, and that would give us the ability to have this really wide field imager. But it requires something very special, something that hadn't really been done before, that I described that single piece of glass. So that was the start of that idea. And so that came out of the University of Arizona, which is where where the mirror was made, in the mirror lab there, which is right under the stadium. So through the 2000s, the National Science Foundation, through our National Optical Astronomy Observatory, as it was called at the time, now we call that MARLAB, they were one of the founding partners in starting that development of the telescope, along with the Department of Energy, which had a lot of interest in the science behind that. And they've had a great interest in doing the camera end of things. It's lined up with a lot of their skills and the Department of Energy labs. So it involved the Department of Energy labs, the National Science Foundation, our national observatories. It involved many universities, like I mentioned, the University of Arizona, the University of Washington, Princeton. There were other ones, of course. Even Jet Propulsion Laboratory contributed to some of the software development. So this was over the 2000s. That's when they built the mirror, and that came from private funding. So we got funding from the Charles Saloni Foundation and Bill Gates, right? These were two important Microsoft founders, and they donated about $30 million between them. That led to the creation of that piece of glass. So that retired a very important technical risk, because a lot of times do you take a risk with this project? What if that fails? But they retired that risk. So by the time it was time for NSF and DOE, who built the camera, when we were getting ready to put it in our major research equipment and facilities construction line, which was ultimately around 2014 when construction started. So the years leading up to that, you do preliminary design reviews, a final design review before it gets into that position. But that risk of building the mirror, and the mirror was already built by the time we started construction. Construction then went pretty smoothly, and then COVID hit. When COVID hit, we were about 2 years away from getting done. So we expected to be done in 2022. COVID added another 3 years with all the delays that came at that point and the complications that were put on top of it. So, as you know, we finished construction last year, essentially, substantially. The first look images came out in June of last year, and we're very excited. Very exciting event around the world. The operations team took over the operation of the telescope last October, and the first alerts, we haven't talked about yet, we will. It came out in February, and the survey started just the end of June, June 29th of this year. So it's a very exciting time. And we look forward to all the results that we're going to get out of it. That's the basic timeline. I came into the picture in 2016. So I've been overseeing the project as the on the NSF end of things since 2016.
Very cool. And indeed, very exciting time. I was going to ask you about the data. Is use or access to the telescope available outside of the legacy survey of space and time? Or is it more of the data that's collected can be used by different astronomers for different projects?
Okay, yeah, so there's a couple issues. First of all, there's data rights to the survey. And then, and so we'll cover that. But the other issue is, and I'm not sure if you're getting at this too, but can you use the telescope to do something other than this survey? That one's a little easier. So let me actually talk about that. But sometimes there are targets of opportunity, as we call them, right? Something is like, hey, there's something really interesting here, and we need a quick survey of this part of the sky. And you can imagine if there's a gravitational wave detected, right, by other NSF facilities like LIGO, right, which is there to define black holes merging and things. If those things happen, and we have the ability, the director has discretionary time, and he has a whole system actually set up to for these types of requests. And it's not a big job for this telescope to do a quick survey of the sky in a certain part, to cover a certain area of the sky with certain filters, because we're going to do that anyway. So it really doesn't take away much from the survey. It changes the cadence of where you're pointing the telescope at a particular thing for maybe a few nights, but it really has almost zero impact on the survey. And so it is something that we are able to do with any kind of interesting follow-up. So that part is fine. This is getting back to the other part of the question. Who has access to the data? Well, every U.S. scientist has access to the data as well as Chilean scientists. But that's not all. We really want the whole world to participate in any way they can. And to get money back on our investment, or at least to sort of balance things out, what we worked out is it for international participants to get the same data rights as U.S. and Chilean scientists if they're offering something of value to the U.S. community in kind. So they can offer telescope time, they can offer software. In the case of the United Kingdom and France, they offered a huge amount of computing resources. In fact, between the U.S., UK, and France, they're going to be doing about half of the, maybe even more, of the data processing every year for all of these data releases that are done. So they're offering a lot, and in exchange for that, they get to have a nice list of scientists who have access to the data. So in the end, there's about 43 institutions that have made such agreements around the world in covering 28 countries. So besides the U.S. and Chile, 28 other countries, and it amounts to about thousands. I don't know exactly what the number is today, but about thousands of other scientists around the world will have access to data. Almost anybody who really wanted it worked out some kind of deal to exchange something in kind to the U.S. community in exchange for data rights. So it's really good. And the data rights are only applied for the first 2 years. So once the data release comes out, once the data are out, they're proprietary to the data rights holders for 2 years. After 2 years, then anybody in the world can access the data. So, you get the data rights have first dibs on publications and discoveries, and then everybody's got access forever after that.
That makes sense. As part of that alert system, you might have, say, a keyword that I'm studying supernova, let's say. So I might have flag me anything that looks like it might be a supernova in that system. And then I might follow up with Gemini and have it look, for example.
Yes, that can be done, of course.
So thinking about this over the next few years, like you've mentioned some of these things, supernovas, what kind of discoveries are you imagining we're going to get in the data in the next couple of years?
Well, there's going to be sort of the low-hanging fruit, right, as you might think of it. We're going to be discovering millions of asteroids. And I say, well, why we know there are asteroids out there, but they're some of the closest things in our universe, right? They're right in our solar system. These could be leftover things that from the formation of our solar system, and yet we don't really. There's so many we don't have a catalog, right? They're too faint. They're too hard to do with other surveys. I mean, you can do a survey and find some, But unless you have a really powerful survey instrument like this, you can't get as many as you can. So we're going to clean up in the next couple of years and finding millions of these asteroids. And what happens when you do that? Like, oh, well, who cares? You found a bunch of things and you catalog them. Well, this is why astronomers keep doing surveys, because you never know what you're going to learn from them, because you always uncover things you didn't know were there, because obviously you had surveyed them before. So and when you have great numbers, you start finding things that, you find one thing, it's an oddball, you don't have an explanation for it. Now you start finding many, many, many of them, even though it's maybe a really tiny fraction of all of them. You now you have a whole population of things you didn't know about, or now you can learn enough about what caused them, where they come from, what are their origins. So that's how we learn how our solar system formed. That's how we learn how other star systems form their planets. And, if you care about life in the universe, if you don't understand how your planets are formed, you really don't have any insight onto how much other life is there out there. These are the way scientists put the objects, put pieces of the puzzle together. And so this will be contributing that way in the first few years. And even the first look event of over a year ago now, right? There were thousands, and just that little image that they took. I don't want to make it sound too little, but
And
it's
there's that great tool where you can zoom into it. It's like, it's not very little.
right. It's not very little when you zoom in. But that they found in just a few nights, right? Essentially, thousands of asteroids. So those are going to just keep coming out for the first couple of years until you have them all cataloged, all the faint ones that we're going to be able to detect. And then there won't be as many. But that will, after a few years, so that's going to be there. The supernova, they're going to be coming out all the time throughout this. So those are just things to be expected. But as I said, what often happens, if more things you identify and you start finding a million of them, you're going to learn a lot more about supernovae. And when you want to learn about dark energy, we'll connect you to that dot a little bit. That's how we started imagining dark energy. It was from all the supernovae that were detected. Now, these were done in a far more manual process in the 1990s, where these images had to be taken, that they had to be compared against the templates to find them, and then you had to do follow-up. But now that's all basically automated, and we will learn a lot more about supernovae. And if the supernovae change over distance and over time, right, this is something that was addressed heavily in the initial days to really try to nail down whether dark energy was real or not. And as best we could do at the time, that seemed the answer. We thought we understood the answer to that question, but it's still, those questions are never totally closed, because there's thousands of people doing follow-up, and they're getting the data. I could say free, but this is never free, but it's going to come easily to them. They will, all the scientists will get data without having to do to request telescope time and to go through all of those kinds of things. They're just the data will be available to them. So many, many investigations will go on, hitting all areas of astronomy and astrophysics. And so the discoveries, I can't even mention what they're going to be, because I don't know, but there will be a lot of easy stuff that comes out. And, because we're going to have incredibly deep images of all these galaxies and clusters of galaxies. That is just great resource for astrophysicists to investigate other investigations to dark matter. And the shapes of galaxies, those are the things where we really do want those 10 years. We really do want those 800 images, and to really nail down those shapes of the galaxies, because that's another way we investigate dark energy. How the lensing from the dark matter and dark energy affect the shapes of our galaxies. And until you have that whole sky view that's really faint, and all the systematic things are investigated, you don't really nail that down too well. So some things will come out early, and some things will take a lot longer time.
Right. It'll have a legacy beyond the actual 10-year time, just as people try to sift through 10 years worth of data. Like, even if you're looking at one specific spot, the amount of detail you'll have with that time scale is going to be amazing.
Yeah. And I think the thing that what a lot of people don't realize is, when you have telescopes that are driven by a telescope time allocation, right? The way a traditional thing is done, you put in a project proposal, and it gets reviewed by peers, and the best ones, right, get the telescope time. And And many other good ideas don't, right? Because the best, it kind of changes with time too, because you have certain interests on what things you wanted to learn more about, but that's not always the right thing to learn what should be learned about. So this is kind of covers everything. And so some of the things that you would never get telescope time to do because it's always a limited resource will be done with this telescope, right? So like in the ultraviolet end, near ultraviolet end, far blue end of the spectrum, it's really expensive in telescope time to do. It's usually not worth it, right? It's hard to justify. So if you really want to learn about stars that, and those are maybe hotter stars that you'll see there. I mean, I'm oversimplifying in many ways, but if you wanted to investigate the variability of such stars, how would you do it? You'd have to have a small dedicated telescope, and not too many people have that, and they might want to be doing something else. So there's certain variations in stars that we would never really have telescope time to do that's going to come out here free of charge, or no additional charge, put it that way. And when you have that, the things that we were going to figure out over decades, and it's not going to happen immediately, are really unknown. And how important are they? Well, I don't know, because if we thought they were really important, you would have done it. And so it's those things you didn't realize were important that will be found in these data and from this survey. So, and slowly varying stars, there are any more stars that vary in ways that we never were able to measure before, because you're kind of fishing, right? Fishing for something. Well, maybe it's there, maybe it's not. Give me telescope time. I want to check. You're not going to get telescope time for that, but it's going to be, again, it comes along with that no additional charge here. So we're going to find things that we didn't expect because of that. And so that's potentially exciting, because you might learn about how our own star and how stars generally evolve, that things that we didn't know were important turn out to be important in the physics that we sometimes, when you make models of things, eliminate. And so I think those are the types of things that will be fascinating that happen throughout the survey and beyond.
It makes me think of the very first interview I did for this podcast series was with the researcher that was looking at Black Widow binary stars. And he was very excited about the potential of Rubin to allow him telescope access, to your point about trying to get access to things, and kind of the depth of information he'd be able to get that he wasn't available at the time to really understand what was happening with these kind of rarely researched kind of stars.
Yeah, it's exciting.
Why is it important that we do this kind of large scale science project?
I think what's easily missed, and it's connected to why you need this kind of telescope and that kind of telescope. One thing that makes science advance, which helps our whole society be healthy and get healthier, and it has many impacts on our lives and makes our lives better, is the advancement of technology and the science that enables. So every time that technology advances, science advances, because we are now pushing the limits of our technology with this system. Well, at some point, this technology will be old, and the new technology will again allow us to push things further, right? Like let's get spectra of all of those 37 billion objects that we're going to find. And every time that happens, it enables us to advance science more. So technology drives the science advances our knowledge of what's going on, which helps us it feeds back into technology. And every time you advance technology, it improves the economy and the lives of people. And that provides the tax dollars that we need to keep letting this stuff happen. Sometimes people are disconnected because we see one thing. We see the health benefit of this, but it's like, well, this doesn't help. How does this help my cancer problem? And it's a legitimate question. Well, the answer is that it's a whole system. So the physics that we might need that we don't realize yet to help the cancer problem has to be uncovered. And until you uncover that, you're not going to get that answer, and you just don't realize it until some roundabout way. That's why I like the unknown things, right? What are we going to discover that's going to lead us somewhere unexpected?
Special thanks to Ed Ajhar. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.